Hello and welcome to lecture 2 of this course on advanced plasticity of solid continua. In this lecture we will be covering the kinematics. We will continue with the kinematic aspects of continuum mechanics. Specifically we will be talking of the transformation of lines, areas and volumes as they get transformed under the deformation gradient from the referential to the deformed configuration. So, and also we will be talking of different types of strain measures, not all of them, just a few, to give you a feel of this, why different strain measures are used. Now, this will be in two parts. In the first part we will be covering only half of the talk, and then we will have a short breather and continue with the other part afterwards. So, please recall some of the things that we discussed in lecture 1. So, we were talking about the continuum modeling, a field theoretic modeling of the mechanics of solids with specifically with plasticity in mind. So, the motion, recall that it is given by a deformation map which is phi as a function of capital X, which is the coordinate cover for the referential configuration, and time t. We also write it as phi tx, as you can see here, right, phi tx or phi of x and t, and the result is the deformed point, which is basically small xt, right. So, recall that capital X is the coordinate cover of the referential configuration and small x the same for the deformed configuration under the map phi. And we also said that more than deformation, the important thing to work with is the deformation gradient, which is the gradient with respect to the deformation the capital X of phi, right. So, basically we have a rigid body motion if this capital F becomes a proper orthogonal matrix which represents rotation. There could be of course another translation which is independent of capital X, only a function of t, but that is not that does not affect this this deformation gradient. So, also recall that plasticity, unlike elasticity, requires the tracking of the microstructure along with the deformation. Without that we won't be able to model plasticity, because it is the defect structure, defect microstructure, that is essentially responsible for plastic deformation. And also we talked about the importance of tangent spaces, that is the most important thing, because recall that F, the deformation gradient, essentially is a mapping of tangent spaces, one located at a material point in the reference configuration and the other located in the image, at the image of that material point under deformation in the deformed configuration, right. So, not directly the deformation map, but the deformation gradient is more useful. So, that itself tells you that the tangent spaces play a very major role here, right. So, now let us talk about the material line elements, how they transform. So, let us consider one such infinitesimal line element dx here, right, in the reference configuration. So, under this is basically the definition of F itself. So, the mapping is such that under F we have d small x here is essentially equal to capital F acting on the vector d capital X, right. So, we have the deformed line infinitesimal element dx, we have the undeformed correspondent, the pre-image of d small x under F, which is d capital X, and the stretch ratio will be given by the norm or the modulus of the vector d small x divided by the modulus of the vector d capital X, right, which is here. This is the stretch ratio, right. So, recall that the stretch ratio is 1 when we have purely rigid body motion. And then the important thing here now comes. So, we can now define, see, we have already said that F in itself cannot be the strain measure, because F is affected by the rigid body motion. So, strain should not be affected by rigid body motion. So, the proper definition of strain one of such strains is the right Cauchy-Green strain, right. It is called it is given by the symbol capital C, and it is defined as F transposed F. You are aware of matrix transposition, right. Think of F as a matrix. So this T denotes transposition of F. Now the Green-Lagrange strain is what is often used instead of this Cauchy-Green strain, which is essentially the given by E equal to half of capital C minus the identity, right, in 3 by 3. What is the identity in 3 by 3? It is 1 0. So in 3 by 3 we have this as the identity, right. Right, that is your I. Okay. So remember here one thing, that both C and E are strain measures, no problem, but they should be looked upon as matrices. I will come to the issue of tensors a little later, but a matrix acts on a vector and produces another vector, right. So here C acts on a material vector like D capital X, right, and produces another material vector. Why is it so? Because you see how the C is defined. So first, you know, in F transpose F, the first action is that of F from the right, right. So F acts on a material vector, produces a spatial vector. F transpose act on that spatial vector to produce again a material vector. So the overall action of C is that of acting on a material vector and producing a material vector again as the output. Exactly the same thing happens with the Green-Lagrange strain E. So that is why we are saying that both E and C transform material vectors to material vectors, right. So these are sometimes called the material tensors, right. So a tensor is basically a multilinear transformation of some object. Let us consider some energy like thing. So let us say phi, not phi really, let us say that you have E, or not even E, because we have already used E. So let me correct it. So let us say that we have some object, call it by small e, which is the energy like object, which basically acts on this all vectors and produces something like a positive scalar, right, R plus, right. So if we consider such a thing, so let us say that E is a function of x1, x2, x3, some functions, right. Then a tensor will be defined as the multilinear transformation of E, something like del 2E by del xi del xj is a tensor. Why is it a multilinear transformation? Because each time I do a partial differentiation with respect to x, I do a linear transformation. A partial differentiation is a linear transformation, right. So because it satisfies the superposition principle, right. So therefore I have done it twice here, so that is why multilinear. So I could have done it once also, then also it will be a tensor, but it is of a tensor of a lesser order. The more you do these kind of transformations, linear transformations, the order of the tensor increases. So here we got a tensor here, which is like a matrix, right, but it is a multilinear transformation on the original quantity, a scalar valued function E. That is why we often say that C and E are both tensors, right. They are essentially multilinear transformations, right. So now let us consider why basically C is a measure of the strain. In order to understand that, let us understand one thing, that consider squared length in the referential configuration. It is basically dx dot dx, right, capital X, you can see it here. This is the squared length in the referential configuration, right. D capital X is a small line element. Now consider under the image of F what happens in the deformed configuration. So we already have seen that D small x is equal to F D capital X, right. So D small x dot D small x will be equal to F D capital X dot F D capital X, right. So this can be written as D capital X dot F transpose by the definition of transposition of a tensor F d capital X, right. So you see this is exactly the definition of C, F transpose F. So essentially what C is talking of here is the change in the squared length of a material line element under the deformation, right, in the infinitesimal sense. So because you can say that d small x, you can write like this, d small x dot d small x minus d capital X dot d capital X. Now you can just write as, how do you write it? It is basically here basically you can write it as d dx d capital X, right, dot this F transpose F is C d capital X minus d capital X dot I identity tensor d capital X. So basically this is d capital X dot C minus I dot d capital X, something like this, right. So that is the reason why you talk of the Lagrange strain in terms of C minus I, right. You remove the effect of the original length, you just think of the change of length, right, with a half outside, that is just to match with the usual understanding of the change of a line element, the way that in the lower classes you have probably learnt about the basic concept of strain, right. So forgetting about that half, the factor, you understand that C is essentially a measure of the change, but a better measure is given by capital E, which is C minus I, right. Okay, so now here comes an important aspect of our understanding of the kinematics of continuum mechanics, which is the decomposition called the polar decomposition of the deformation gradient F. So here is the polar decomposition, let us not get into the proof of this, because I mean you can understand it, but there is no time for us to do that. So F can be written in two different ways. One is in terms of R times U, R is a matrix, U is also a matrix, or V times R, R is the same matrix as in the previous expression and V is also another matrix. What is R? R is basically a proper orthogonal matrix as we have shown here, which is we require that R transpose R is the identity matrix and determinant of R is +1, right, and U is called the right stretch tensor. This U is called the right stretch and V is called the left stretch, right. The important thing here is to understand that while R is an orthogonal tensor, U and V are symmetric positive definite matrices, okay. So I will be using the words matrix and tensors in an equivalent manner, so please understand. So whenever I say matrix, unless it is in some other context, it will always be a tensor, a kind of a multilinear transformation, right. So why do you do this, this kind of a polar decomposition? The reason for this is that we separate in the process two effects of local deformation in an infinitesimal sense. We separate the effects of rotation and stretching. By stretching I mean here not just stretching in the usual sense that you stretch a line it becomes longer, but also stretching here includes the case of change of angle between two lines. So a line can get elongated under deformation, or two lines originally this way under deformation they can change their angle. Both are possible under this stretching, right. So stretching is a more general word here, right. So it separates the rigid body aspect of the rotation. This rotation is entirely a rigid body rotation that goes with it. Also note one more thing, that C can be written now given this F equal to Ru, so C is equal to F transpose F. So this is equal to, so you put C F equal to Ru, so it becomes U transpose F transpose, sorry, U transpose R transpose, okay, Ru. Now you already know that R transpose R is identity, so you can write this as U transpose U. since U is symmetric, so U transpose is U, so you can write this as U square, right, understanding that this is just a matrix multiplication of U with itself. So essentially what this is how then therefore we have a representation of C in terms of this squared stretch, you understand. So the effect of rotation is gone, the R effect of rotation, the rigid body aspect, infinitesimal rotation, that infinitesimal deformation has two parts, rotation as well as the generalized stretching as I have mentioned. So therefore C contains only the stretching part, and so does U, right, both of them. Recall here that in this particular case F maps a material vector to a spatial vector, right. So see what happens to RU. U maps a material vector to a material vector, that material vector is input to R, which maps that material vector to a spatial vector. So R essentially is a material to spatial vector transformation, okay. So a similar logic is applicable for the other part also VR, right. So typically we will be working with RU in our work. So VR is something that we typically do not, the fluid mechanicians are more bothered about this decomposition VR, right. Anyway, so this is just a way of expressing how basically you are separating the rotation effect from the stretching effect. So if you in the reference, if you start with a square like this, a small square, even though it is written in a big way, I mean over a long area, but think of it as an infinitesimal square, right, always, because these are point-wise information. U changes from point to point, R changes from point to point, F changes from point to point. So therefore, you cannot go too far away from a point, right, in describing the effect of R and U. So therefore you just start with this, and then you see under the action of stretching we have a stretching of this, we have not shown the angle change, but assume that it is there, right, and a rigid rotation of the whole thing comes afterwards, right. So this is the two parts of the components, two components of the deformation that come, and this stretching is an important thing. This splitting of stretching and rotation is an important thing because it comes directly in the definition of the strain, as you saw in the last slide, right. Now we come to the issue of, so we have discussed about the change in length, right, under the deformation map phi, specifically under the deformation gradient F, which is derivable from phi. Now let us talk about the volume change. So the volume change essentially is directly organized using the Jacobian, that is the determinant of F, because as we discussed in the last class, in the last lecture, the determinant of F is essentially a descriptor of changes, local changes in volume, right. So therefore it is a ratio of the modified volume to the original volume. So essentially we can simply therefore write that if we define J equal to the determinant of F, remember that this is always greater than 0, otherwise 2 points can merge with each other upon deformation, which were separated in the reference configuration, which is not allowed. Interpenetration, that is called interpenetration, which is not allowed in mechanics of solids, in the continuum mechanics of solids. So now based on this we can clearly say therefore that this J determinant of F is a ratio of this d small v divided by d capital V. Think of dv, d small v, each one of these dv's as scalar objects, right, change in volume, right. So therefore this is directly the definition of J determinant of F, right. So d small v, the deformed volume, infinitesimal volume, is related to the undeformed infinitesimal volume d capital V through J. And J greater than 0, in addition to this inner interpenetration avoidance, it also ensures orientation preservation, right. It preserves the orientation. That means if you are working with a right-handed screw system, corkscrew system, then upon deformation it does not become left-handed. If that is the case, then we say that the orientation is preserved, That is an important thing. You want to work with a similarly oriented coordinate system in both undeformed and deformed, reference and deformed configurations, right. What does j equal to 1 mean? So, j equal to 1, you see, requires that the volume after deformation d small v is the same as the volume before deformation. So, j equal to 1 means there is no volume change because of the deformation. So, this j equal to 1 is typically used for incompressible materials which only change their shapes upon loading or upon straining, but not their volume, right. Water being soft tissues, tissue like material, rubber being an example, right. So, rubbery materials are examples. These are called sometimes hyperelastic materials. I mean, these are examples of hyperelastic, but we do not talk about hyperelasticity here, right. Now, we come to the issue of transformation of area, because we have talked of transformation of lines under deformation, transformation of volume. Now, we come to the transformation of area. This is a little more slightly subtler. So, you know that any small area element, it can be for example, think of a small area element somewhere. So, it can be denoted as well as represented. If this is a small area element dA, it can be represented in terms of the normal vector, right. So, an area element can be therefore thought of as a vector represented through the normal vector, you know this, right. So, when we say NdA is a small area element, as we say here, it essentially means that we are talking of this dA as a scalar and this n is a vector. So, together it is a vector, right. The interpretation has to be right. Now, think of this referential area given by this NdA here, okay. This is the referential area. Now, under deformation, how does it transform? That is the question, right. So, what actually happens, let us say that upon deformation we have this new area element dA times, because d small a is a scalar, times the new vector, normal vector n in the deformed configuration. These are essentially all in the tangent spaces, right, because you basically talk of the body, you take a point, fix a tangent space here, take a small area here and then draw the normal. This is how we do, right. So, these are all about in the infinitesimal neighborhood of a point. You must always understand that. That is why we always talk of this dA, right. Now, this area element in the deformed configuration can be written as the cross product of two vectors, These two vectors are nothing but dx1 and dx2, right, because these are the coordinate cover for the reference the deformed configuration, dx1 and then another vector dx2, right. We do not write it dx2, right, and this is n, this is my dA, right, sorry, dA, right, this is my dA. So, now this dx1 can be written as f capital dx1, the pre-image of this, because that follows from the definition of the deformation gradient, and similarly f dx2 for the other. Now, we use a key algebraic identity which actually is very easy to derive, but let us not right now do that. If time permits, I will come back to this. So, the identity that we use now is the following. For any two material vectors u and v here, right, fu cross product with fv is given by the determinant of f inverse transpose times applied to u cross v. Now, u cross v is the area element in the undeformed configuration, because u and v are vectors in the undeformed configuration, right. So, you see what this, if I call this as the cofactor matrix FC, right. So, what the FC is doing is that it is acting on an area vector, because areas are vectors, normal vectors, right. So area vector in the undeformed configuration to produce an area vector in the deformed configuration, right? So this is the transformation that we wanted for area elements. So therefore this is called that's why we get the what is called the Nanson's formula. But remember, determinant of f we called as J, right? Determinant of f is J. So essentially the cofactor here is given by Fc is equal to J F inverse transposed. Remember that f is invertible because the determinant of f is always greater than 0. Okay, so the Nanson's formula relates the deformed area element to the undeformed area element through the cofactor, right? That's a very important thing because stresses, when we define, stresses always act on areas, right? So the transformation of stresses, if you are interested, you will be naturally required to look at these kind of formulas for transformation of area elements. So with this we come to the end of the first part of our lecture 2. We will now have a short breather and come back afterwards. Thank you.